So right after your book finishes up with molten, and they tell you that all molten substances can be electrolyzed except a few which actually decompose before even they melt. For example, copper to carbonate. After that, they finish it up. The next thing is electrolysis of aqueous solution. And when that happens, we have an activity 5, in which we are going to electrolyze aqueous solutions. In this specific case, we are going to go with electrolysis of sodium chloride solution. And if you're going to look up the past papers, you're saying you will see this to be written as brine solution. Actually, brine was the name of the scientist. He was the first person to use this specific solution. It's actually a salt solution. So brine solution is the salt solution, the daily table salt we eat in NaCl. If I be exact, it's concentrated NaCl aqueous, all right? So that's what brine solution is. So if you see the word sodium chloride solution or concentrated NaCl aqueous or salt solution or brine solution, it means the same thing as per your course. Now, this clarifies that we're using aqueous solution. We're dissolving the salt in water before we're going to proceed with electrolysis. Before I move any further, I'd like to really elaborate here the changes in the diagram. Let's get started with the basic changes. You see the battery at the bottom. Previously, it wasn't. Let me take you back a couple of pages.
It was up, right?
Right, it was on the top side. It was right up on the electrolysis apparatus, whatever that was, whether that was a crucible or a beaker or whatever container we used, the battery was present on top and the electrodes were dipped into the solution or hanged into the solution. So much so that a specific part of the electrodes was dipped into the electrolyte and the rest was out of it. Now, this is totally different. In this case, you would see that the battery is present at the downside. Now, in this case, the battery is present at the bottom. We can see the positive and negative electrodes. Understandable, it's a similar thing. Remember, the positive electrode we are calling over here is the anode. The negative electrode is the cathode. We already know that. Now, we have a rubber bung over here, and on top of that, we have a glass tube. In that glass tube, we have separate test tubes. We can even use boiling tubes. Whatever fits the electrodes or their size into it would be good enough for you, right? So we use concentrated sodium chloride solution in here. Of course, the solution is going to rise up in here, and there are gases produced in this, which we can see clearly from the bubbles. The observations that we see over here matter a lot, because these observations, even if you don't know what's going to happen in the electrolysis, the observations are something that can clearly tell you.
Breaking.
Can you hear me now?
No, sir. Your voice is breaking, like, can't hear that much.
Just a minute. No, I didn't. I
Oh, yeah.
forgot. I'm sorry, I forgot. But a little recap: the positive electrode anode, a negative electrode cathode. Then we have a rubber bung, and we have electrodes fixed into the rubber bung. We can use a test tube or a glass tube. Inside this big glass tube, uh, whichever one suits us, boiling tubes, test tubes, as per the length of this electrode. Now, I was talking about previously the brine solution, which is concentrated sodium chloride solution. So the same thing is written over here. The observations in this case is very important, since we don't know what our products are going to be, but what we can see in front of ourselves is that both the test tubes are showing bubbles or effervescence in them. These bubbles mean that whatever our product is, it is getting collected in the form of a gas. So what makes aqueous solutions electrolysis a little bit more difficult than the molten is that we have the observation to think about. The other thing is that we have the whole background chemistry as per related to anode or cathode, where cations are going to go, where anions are going to go, or where oxidation is going to occur, or where reduction is going to occur. These are the things that we need to keep in mind when going with aqueous electrolysis, which makes the whole aqueous electrolysis a little bit difficult because that's a lot of things to carry at the same time. All right.
Mhm.
A little bit of a safety note where eye protection, do not smell chlorine, especially if you have asthma. Once chlorine is detected, the current must be switched off. Remember, the whole thing can be done in a big apparatus, which we usually call a fume cupboard. A fume cupboard is actually a sealed cupboard which does not let any of the gases out, so that even if we have to deal with a poisonous gas such as chlorine, we don't have a problem. Not all schools have fume cupboards in their labs. In that case, the second alternative is a well ventilated space. Make sure you have all the windows open, you have all the doors open. If possible, turn on the fans. It should be a ventilated space so the poisonous gas does not hurt a specific person. If anybody has any breathing issues or asthma, he or she should stay as far as possible from the experiment where they can see it at least, but they don't have to come in directly interaction with the poisonous gas. All right. Since
Mhm.
it's actually a poisonous gas, we need to be very safe. It's not just a scary thing, it's to scare the students away. Just to be safe, it's actually problematic. So this gas is something we should be very careful about, right?
Yeah.
Now, set up the apparatus as shown in the diagram, glass tube, rubber bunks, electrodes, the whole thing is together called an electrolytic cell. We pour some concentrated sodium chloride solution into the glass tube, place the tube containing sodium chloride solution over each electrode. The test tubes must not be completely cover the electrodes or the ions will be unable to flow and there would be no current. So remember, these test tubes should be a little bit up, all right? So that the water can reach the electrode. If the test tubes are all the way down till over here, of course, the water won't be able to go inside, but won't be able to reach the electrodes. There won't be no flow of electricity. Of course, we won't be able to even start the electrolysis. So it makes sense that the test tubes and the rubber bunks should have some distance in between them.
Mhm.
That's something very easy to understand. And basically, it's physics more than it is chemistry. So connect the battery or the power pack to the electrodes. The experiment should be done in a fume cupboard or a fume hood or a very ventilated room because chlorine gas is poisonous. I've already discussed about it, so this shouldn't be a problem. Now, if you get any bubbles of gas or the metal forming at electrodes, gases can be tested. The tests for different gases will be covered in chapter 18. Let's not go for now. We are going to stick with the observational chemistry. So if there are any gases produced, if the gases are colored, they are very easy to understand because the colorful gases we have in your syllabus are very less. So it's very easy to identify a gas based on its color. All right.
Mhm.
So in both the cases, we see either the anode or the cathode. The gases, he tells you that hydrogen forms at the negative electrode, which is cathode. He also tells you that chlorine forms at the positive electrode, which is anode. Now,
Mhm.
we would expect to get the same volume of hydrogen as chlorine, but in reality, we obtain less chlorine. Why? Chlorine gas is more soluble in water than hydrogen is. Actually, to be honest, hydrogen is an insoluble gas as per your course, so we can expect solubility from chlorine, but not from hydrogen. That's why if you see it in the diagram, on the positive end, you have a little amount of chlorine. See, you have a little amount of chlorine over here. This is Cl2 gas, and you have somewhat bigger volume of hydrogen collected over here. So I hope it
Mhm.
makes sense
Yeah.
what he just said. If a gas is soluble in water, less gas would be collected. If a gas is insoluble in water, more gas would be collected. It's pretty easy of an observation. Okay, so when the molten sodium chloride was electrolyzed, these were the products. It's molten, all right? Now what we are at is the comparison. This comparison is going to tell us the difference of products between the electrolysis of molten sodium chloride and the electrolysis of sodium chloride solution. Now, in case of molten, these are our products. If I actually compare it with case of aqueous, the products are going to be different. And at anode, we get chlorine. At cathode, we get hydrogen. There is another product, but we're going to discuss it a little later. All right. So we're not going to just get two products out of it. In case of aqueous, we're actually going to get three products out of it. Well, let's get started with these two first. Now, when you electrolyze sodium chloride solution, you don't get the same product. You don't get the same product as molten sodium chloride system. Why? Because you have something additional in the system. What is additional in the system? Water. Water is a weak electrolyte. Actually, pure water is a weak electrolyte. Pure water cannot conduct electricity as well as the salty water does. It ionizes very slightly, and it actually gives out ions. Now, this may come as a little bit of a contradiction. How? Back in the bonding chapter, you studied NaCl to be an ionic compound and water to be a covalent compound. Now, you already know as soon as we pass electricity through an ionic compound, right, it immediately breaks down into ions. Why it is made up of ions? It was made up of ions in the first place. So yeah, it's understandable whenever we're going to electrocute it, it is going to be converted into ions. किसी को भी बिजली के झटके दें सब कुछ चला जाता हो जाएगा. Although that sounds funny, but yeah, it makes it easy for my students to understand that what electricity does to molten compounds. So yeah, it would be converted into separate ions, the positive ions and the negative ions. All right. So moving on with covalent. Now, covalent compound H2O is not made up of ions. So it should not break down into ions. But what you're going to see in case of water is different. As soon as electricity passes through water, it actually breaks it down into ions. So water is going to give you somewhat a unique behavior. And you're going to get ions, which water wasn't made up of. Water was made up of covalent bonding, sharing of electrons between oxygen and hydrogen atoms. Right? But when we electrocute water, when electricity is passed through water, instead of giving separate atoms, it actually gives us ions, a positive hydrogen ion and a negative hydroxide ion. Okay. Now, there is a reversible sign shown over here. It's that the water molecules break up to form hydrogen ions, and these ions may recombine to form water again. So whenever you have water present, actually you need to consider these ions as well. That's what makes the whole product different. Why? Because previously you only had two ions to work with, a single cation and a single anion. Now you have to work with four. Actually, you have two cations and you have two anions. And when there is a single person running, he's always the winner. But when there are two people running, it becomes a race. It becomes a competition, right? And one of them has to win, the other one has to lose. So one of them would be able to get to the electrode and leaves the system in the form of a gas, the other one would not be able to. Now, As soon as you see these aqueous products, it clearly gives you the idea that among the anions, Cl negative versus OH negative, this one went to the electrode, anode, and went out of the system in the form of a gas. And when I talk about the positive ions, Na positive versus the race between H positive, we see H positive to get to the cathode and leave the system. This wins the race. So think about it more like a race, a competition of getting to the electrode and leaving the system. Make sense?
Yeah.
So now, if we are doing electrolysis in aqueous solution, which means this side is going to be the same every single time because every salt will be dissolved in water. However, these ions can be different. So every positive ion has to compete with H positive, and every negative ion has to compete with OH negative for this race. And in different cases, different ions may win. Out of 4 total ions, 2 of them will win. One of that will go to anode, the other one cathode, and 2 of them are going to lose. These two lost this race. They were never able to get to the electrode. The kind of understanding we give to the students at this point, although that's not entirely true, but at this point, for the ease of understanding, that can be a really good example. Make sense?
Yeah.
Okay, so now every time you are given an aqueous solution, you are going to convert it into ions. You'll get 4 ions in total, 2 positive ions, 2 negative ions. You're going to take them like a race. 2 ions, 2 positive ions competing for the race to get to the cathode, and 2 negative ions competing for the race to get to the anode. That's how you're going to solve this question. I am going to give you the rules of which ions are going to win at cathode, which ions are going to win at anode, and every time it would be easier for you to decide who is going to win the race, right? For example, if you talk about your class fellows, and there is actually an athletic race sprint competition at your school, you'd probably already know among the participants, among the competitor, who is going to win. You'd probably had an idea about someone, yeah, he is definitely going to win the race. He or she runs faster than the other person, than his or her competitors. And of course, he or she is going to win, right? You can make a guess. You know who can run faster or who runs slower, etc., etc., right? So
Yeah.
if I give you the idea already about the cations for the race at cathode and the anions about the race at anode, the whole thing can become really easy for you. Every time you'd know who is going to win the race. And if you know every time who is going to win the race, you definitely know what the product at cathode would be and what the product at anode would be, right? And if you know it every time, your guess about the product is going to be correct every time. And once you have the correct guesses, later on, it's going to be a piece of cake because correct product means you can write the correct equation, which means correct answers for oxidation and reduction reactions. And finally, correct observations about those reactions, meaning getting everything right. Make sense?
Yes, sir.
Good, good. So what I'm going to do is that I'm not going to proceed with the book right now. Instead, I'm going to give you the rules
All right.
so that it's easier for you to decide who is going to win the race. I'm going to stop sharing this for a quick minute. I'm going to open up the other document. All right, the same document that I sent you earlier, which started off with electrolysis tables. If you go below that document, you have electrolysis of solutions, and you actually have those rules. The rules for cations are separate, and then there are rules for anions. You may see too many rules, but I'm going to cut it short for you in 3 simple rules. All right, so let's
Yeah.
start with those rules. Now, first of all, the rules for cations. Before I get started, remember, any positive ion was versus hydrogen ion. Why? Because the water is every time going to give you hydrogen ion. So whichever salt you're using, you may get a positive ion out of that salt versus hydrogen ion. So everything has to race against hydrogen. The rules for cations are simple. We use the reactivity series. This page number is different because it's talking about a Cambridge book, not an Edexcel book. All right. So if the salt name or the salt formula consists of elements such as copper, silver, gold, or platinum, they are deposited at the cathode. Otherwise, if the salt is made up of any other element, sodium, calcium, magnesium, aluminum, potassium, lithium, iron, zinc, lead, anything else, hydrogen would be produced at cathode by this reaction. And it's really easy. You just need to remember the names of three elements: copper, silver, gold. Why? What's the reason behind it? The more reactive ions tend to stay inside the solution. It's not barium. This is wrong. It's actually brine solution, and it's concentrated NaCl aqueous, not NaCl2, right? So more reactive stays inside the solution, the less reactive goes to the electrode, which means copper, silver, gold, which are less reactive on the reactivity series than hydrogen, tend to go to the electrode. Otherwise, every time, since all other ions are more reactive than hydrogen, they tend to stay in the system, and hydrogen tends to leave by going to the cathode and leaving as hydrogen gas, right?
So, sir, those elements which you said, those will um
Stay inside the system.
uh-huh.
Something would happen to them, but we're going to discuss that a little later, not now. So keep that question hanging on for a minute, and I'll be getting to that real soon. This is not genetic rule, it's a generic rule. There are too many mistakes. This is a generic rule for ions that more reactive stays inside the solution and the less reactive gets to the respective electrode. So that's why copper, silver, and gold are going to the electrode, or hydrogen is going to the electrode if there are any more reactive ions present. Now, back with NaCl, you knew that there was Na positive ion versus H positive ion. So H positive, being less reactive, went to cathode, and Na positive, being more reactive, stayed inside the system, right?
Yeah.
It might make little sense now, but as soon as I finish the rules and try to go with a couple of examples, the whole thing will become crystal clear. Now, rules for anions. In case of anions, there are actually two kinds of anions. These are for simple anions, and the anions may consist of more than one atom. So these are for polyatomic anions. Poly means many, atomic means atoms. So polyatomic anions are anions that consist of more than one atom. Okay, if we have simple ions like chloride ion, Cl negative, bromide ion, Br negative, or iodide ion, I negative, if they are versus OH, and remember, from water we get OH negative ion. So any negative ion will be in this race with OH negative ions, because water is going to give us OH negative ion. In this case, it really depends upon the concentration of solution. Now, there are no negative ions in the reactivity series. So this definitely has to do more with concentration than it has to do with reactivity. At least at this stage, we discuss it in terms of concentration. So if the solution is concentrated, the halide ion, the halogen, will be produced at the anode. If the solution is dilute, OH negative goes to the anode and it forms oxygen gas with this equation. You're supposed to memorize this equation. This equation is going to help you a lot. All right.
Yeah.
In case of polyatomic ions, these are the polyatomic ions. Nitrogen, you can see it is made up of many atoms. One nitrogen, 3 oxygen atoms, carbonate ions, 1 carbon, 3 oxygen atoms, sulfate, this is a capital O definitely, it's a mistake. Sulfur, 1 sulfur atom, 4 oxygen atoms, phosphate, 1 phosphorus atom, 4 oxygen atoms. So they're O versus OH. In that case, every time oxygen is produced by the same reaction, these two reactions are exactly the same, which means in case of anions, it's most of the time oxygen gas being produced at anode. All right. These
Mm-hmm.
look like a lot of rules. I'm going to wind them up in 3 simple tips, but we're going to do that a little later. Let's keep on going with the concept. Now, tips for anions: if the salt name consists halogen and it's concentrated, a halogen will form at anode. If the salt name consists of the word dilute, it means oxygen would form. In case of polyatomic ion, oxygen would form. So most of the time, it's oxygen that is formed. And
Mm-hmm.
again, there is a huge table of possible examples that from past 10 years of papers, and you are possibly not going to get an example out of these. All the possible examples have been discussed over here. All right. Now,
Mm-hmm.
this gave us the idea. I am going to clarify this idea by using this white portion, and I am going to give you 3 simple tips. Now, let's divide our tips for cations, simple anions, and polyatomic anions. All right.
Mm-hmm.
Now, if the salt name consists of copper, silver, or gold, only then these elements are produced at electrode, cathode. Otherwise, if these names are not present as a part of the name of the salt, hydrogen will always be produced at cathode. That's it. That's how easy the cathode product is.
So why though?
Sorry, I didn't get that.
Why only these three, not
Because
other?
on reactivity series, these 3 are below hydrogen.
Oh, oh,
Since we're
all right.
comparing everything with hydrogen, so only the ones that are less reactive than hydrogen get to the cathode. The ones that are more reactive than hydrogen, they don't bother running to get to the cathode. They know they are more reactive and they'll find someone, some ion to react right over there. They don't even bother running for the race.
Ah, yeah, okay.
You see, there are some people in the class who are not ecstatic at all. When the athletes are trying to work their blood and tears at the same time to win a single race, the non-athletic people are staying out of the ground and they're saying, we don't bother to race, we don't like to race, we're not athletic people, we like to eat, we like to stay fat, or whatever their reasons are. I don't know. I'm not being biased, but yeah, there are some people who never care about the races. The reactive ions are like this. They are so reactive that they don't even bother about going to the cathode. They keep on imagining the same thing and they actually do it like that. They say that we will react with something right over here. Why do we have to run to the cathode? So the less reactive one tries to win the race and wins alone. So there you see hydrogen going towards the cathode and winning the race and uh, converting itself in the form of hydrogen gas, right?
Yeah.
So whichever salt name is there, if the name of the salt does not consist the words copper, silver, or gold, you're always going to write hydrogen as a product. So look at this table. Most of the time, hydrogen, 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 hydrogen. Why? These are filled with sodium, potassium, and stuff like that. Until unless I come to silver, as soon as you see silver over here, silver is getting produced. Otherwise, hydrogen, 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 hydrogen. List is all hydrogen until
Mm.
unless you get to copper, and there you go. In the list, you see copper. Otherwise, this list is filled of hydrogen as a product. So most of the time, it is going to be hydrogen as a product at cathode. So why worry about the whole big aqueous electrolysis? Too difficult, too difficult. No, it's not too difficult. At this stage, at IGCSE, it's too easy. Apart from these three elements, every time hydrogen would be produced at cathode. Why worry?
Mhm. All right.
Anyone can see or look out for the name or the symbol in the formula and then can easily tell that hydrogen would be produced at cathode if the name does not consist of these three elements. Easy enough, right? That's the
Yeah.
first step. Now, in case of second tip, we talked about halogens, chloride, bromide, or iodine. Now, their race is versus OH negative. Now, these
Mhm.
are going to win if they are concentrated. If they're concentrated, they win, all right? And if the
Mhm.
system is dilute, this wins, all right?
So,
If
sir,
this wins, this is going to be converted into oxygen gas at anode. And the equation is this equation every time. This is the equation that we memorize for OH aqueous. It gives us two water molecules, which are liquid. It gives us one molecule of oxygen gas, and it is going to give us 4 electrons. This is the equation that you are going to memorize. And every time it's a dilute system, you write this equation no matter what there is. If it's a concentrated system and has the words chloride, bromide, or iodide, then you're probably going to produce chlorine, bromine, or iodine. In case of polyatomic ions, whatever polyatomic ion that is, and there can be many, whatever that is, every time OH negative wins. Every time, no matter what the case is, and wins to give this O2 gas, right?
sir, why always OH wins?
OH is less reactive. Easy.
Oh,
The
also
more the
it's
number
very.
of oxygen atoms are in an anion, the chances are the more reactive it is going to be. The more reactive, it won't bother to get into a race. It would like to stay there and find some reactive stuff over there, OH negative, which is less reactive, then runs for the electrode. And there you go. You have oxygen produced at the electrode. You also get water as a product, but since there is a lot of water already there in the system, we started off with an aqueous solution. We don't care about water being a part of the product, so the only product is considered oxygen gas.
Sir, what if an element is same reactive as OH? Then what happens?
Actually, that's not a case that we discuss at IGCSE level, so don't worry, you're not going to get a question like that. But yes, we do answer that question at A levels.
All right.
This is something more difficult. It definitely needs some advanced level approach. So let's keep that question for now for A levels because we need to explain a lot more things before we can get to that answer.
All right.
See, we have already started to give you an idea that concentration and reactivity both matters in case of anions. So yeah, it's not just the reactivity that wins. Concentration also plays a role. So before it gets too difficult or too complicated, we actually drew a boundary line for IGCSE students to keep it simple, to keep it easy for now. In advanced levels, yeah, we'll discuss the complications and we'll tell you how the result is going to differ.
Mhm.
Or
All
what's
right.
going to happen if you have two things or two ions of the same kind of charge. I mean, if they both are negative ions and if they both have almost the same kind of reactivity, and let's for the sake of our question say they both have the same kind of concentration in there, who's going to win? Yeah, we need to discuss the possibility, but that's an advanced level stuff. And we'll definitely discuss it over there.
All right.
Okay. So
Yeah.
3 simple tips. If the salt name consists of these positive ions, hydrogen would be produced at cathode. the other element will stay at in the system. If you have these halogen-based ions, anions in the system, and the salt is concentrated, this halogen would be produced. Otherwise, you'll produce oxygen as the result of anions. Because most of the anion cases, we produce oxygen by this specific equation. And let me take you a little below on the table. See, chlorine as a product, oxygen, iodine, oxygen, 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 chlorine, bromine. So the only four possible products are chlorine, oxygen, bromine, and iodine. That's about it. There are no other products. So we don't have a big list of products for aqueous electrolysis. Aqueous electrolysis might seem difficult to students. That's I actually say that is because the teachers are not able to explain it properly to the students. If you have these three simple tips, you would know every single time what the product is going to be. Now,
Right.
you remember I was talking about there are not just two products in the system, there is a third one. Take a look at
Yeah.
the table. The change to electrolyte is not used up anymore. We are producing something new in over here. Sometimes something new, sometimes the same stuff. So how would we know we are producing the same stuff or not? Whichever two ions win and go to the cathode and anode, the rest of the two react together to give you the product. Take a look at
Oh,
concentrated HCl. Now, concentrated HCl, it's pretty simple. Now,
yeah.
NaCl aqueous gives us Na positive ion. It gives you Cl negative ion. Now, since it's aqueous, aqueous means there is water. Water is going to give you H positive ion. Water is going to give you OH negative ion. So there are a total of four ions. Now, let's consider it is concentrated, like this example. So, of course, we're going to get hydrogen gas at cathode. We're going to get chlorine gas at anode. Now, what are we left with if you take these two out because they went to the electrode? Consider this one and this one reacting. So Na positive reacts with OH negative, and this literally produces NaOH. Combine both of them, and there you go. You have the changed electrolyte. Because the electrolyte is only left with two ions. Those two ions react together. They may form something new. They may not form anything new. Easy enough.
Mm. Yeah.
So that's what it is. So every time, try to write these four ions. One of them will go to cathode. This one, hydrogen goes to cathode. Chlorine went to anode, right? And
Yeah.
these two combine to give us the change to electrolyte. This is what this table consists of. The product at cathode, the product at anode, the change to electrolyte.
All right.
So this big table is going to help you with a lot of examples other than your book. But for now, what I'm going to do is that I'm going to get back to your book by clearing all of this up. Okay. Now let's talk about what your book says. So at the cathode, we have these two ions, sodium ion and hydrogen ion. Sodium is a very reactive metal. It is very difficult to add an electron to sodium and to convert it back to sodium atom. Hydrogen is far less reactive. It's very easy to add an electron to hydrogen, and hydrogen is the one that goes to the cathode, loves to get an electron added to it, and becomes hydrogen gas. Since it was less reactive, it was ready for a change. It got some electrons added to it. It changed from an ion to an atom. There you go. You have hydrogen gas at cathode. The book gives you a deeper dive. All right?
All right. Yeah.
Good. The more reactive something is, the greater tendency it has to form an ion. This means the more reactive something is, the difficult it is to turn back into an atom. For positive ions, the lower the position of element in the reactivity series, the more easily it is going to accept an electron. And that's why the bottom of the list, copper, silver, gold, or hydrogen, accept an electron. The rest do not. Since sodium, calcium, magnesium, potassium, lithium, iron, zinc, they're all on the top of the reactivity series, they tend not to be converted into an atom. However, the bottom four elements, H, Cu, Ag, Au, I mean hydrogen, copper, silver, gold, since they are the least reactive ones, they'd love to get electrons added to them and become atoms, right? So what happens, water was broken down into H and OH. H got some electrons and was converted into hydrogen gas, which was given out at cathode. We have OH negative ions left in the system. So there is a buildup of OH negative ions around the cathode. All right. Why they are
Yeah.
leftover ones? An alternative way of looking at this cathode reaction is this. Water gets some electrons, it produces hydrogen gas, and it gives a lot of OH negative ions. The ions that left in the system and were never able to get to the electrode. All right. We
Yeah.
call it an ionization process. Yeah, it's easier to understand that way. Now, the other case, anode. Cl negative and OH negative are both attracted by the positive anode. It's slightly easier to remove electrons or oxidize these. Now, fluoride ion is much easier. Why? Because they were present in more concentration. Remember, we started off with concentrated NaCl aqueous. Concentrated means there is more salt, which means there would be more Cl negative ion, which means we'll go with this one. If the sodium chloride solution is dilute, that means there is more water. Then when there is more water, there are more OH negative ions. Then we are going to be proceeding with this equation. So memorize this equation. You will only be asked to write this equation in exam, not the reason about it. All right,
Mhm.
as mentioned over here. Okay, so if it's concentrated, you're going to produce the halogen. If it's dilute, which we usually mention like this, or we may mention the whole word, dilute means there is less salt, there is more water. When there is more water, there are more OH negative ions. Then this equation is going to happen. Concentrated means there is more salt, less water, which means there are more Cl negative ions. Then this equation is going to happen. Here, the majority wins. I call it a democracy. The more number of people, the more ions in the system, they win. It's that simple, right?
Yeah.
Okay, good. Now let's clear everything up. What happens to the remaining solution? Now from NaCl, we got these two ions. From water, we got these two ions. Now we're cutting out chloride negative because that went to the anode. We're cutting out H positive because that went to the cathode. Now, these two ions went to their respective electrodes, got discharged in the form of gases, respective gases. What are we left with? We're left with Na positive and OH negative. They're going to react and they're going to give you the sodium hydroxide solution. Good enough?
Yeah.
That happens. Whichever two ions you're left with, react them with one another and form your product. That is known as the change to electrolyte or the remaining solution in the system.
So what about product?
This is a product. The
Okay.
remaining solution is one of the products. Okay, let me take you back to make this the answer to this question more easily understandable. Okay, let's get back to the diagram. Now, you will get one product over here at anode, one product over here at cathode, and this solution in the system will be a third product.
Mm-hmm.
So this gas is chlorine, this gas is hydrogen. The solution is not now just NaCl, it's actually sodium hydroxide. So you have three products out of this electrolysis. Remember, molten system gave us two products only, the metal and the non-metal. This one is giving us three products,
Mm-hmm. All right.
right? That's
Yeah.
how easy it is. If you remember the three tips about the cations, all right, about
Mm-hmm.
the anions, you are going to get it right every time. Think about
All right.
the second example, copper sulfate solution. Now, copper sulfate, as the name says, it has copper and it has sulfate ions. Copper is these ions, sulfate are these ions, and they're coming out of this system, all right, this formula. And it's aqueous, which means there's also water. So aqueous is going to also give you two ions, H positive and OH negative. Now this is competing against this is competing against this. Now I've already given you three tips. My first tip was if the name of the salt or the formula of the salt tells you about the presence of copper, silver, or gold, copper would be formed at cathode. And you see the same product at cathode. The cathode has red brown copper on it or pink brown copper on it, right? And I told
Yeah.
you if there are multiple atoms in your anions, polyatomic, like SO4 negative 2 has 5 atoms, then OH negative is going to give oxygen at the cathode, at the anode, my bad, anode. So yeah, you have oxygen bubbles at anode. It's how simple it is. And you'll of course memorize the equation for oxygen. Copper equation is going to be simple. Since it's +2, add 2 electrons to it, you get copper. This is reduction, this is oxidation. And the rules are again the simple. Anode gives you the oxidation reaction and cathode gives you the reduction reaction. So this is similar as it was back in molten electrolysis. All right,
Yeah.
good. So this gives us the idea about the three products we're going to have. Now, so what about the third product? There are a total of 4 ions over here. This one went out in the form of oxygen. This one went out in the form of copper. What are we left with? This one and this one. React them together, and you're going to get sulfuric acid, H2SO4. So take a look at this equation. Where did the equation go? I have no idea. See below. Where is below? Where is that
Sure, it's
below?
not there.
It's not here. Yeah, there it is. No, actually,
Wait.
unfortunately, no. No. This is copper sulfate aqueous. It tells you how copper forms at the cathode, how oxygen forms at the anode. It unfortunately does not tell you about the change to electrolyte. These are like incomplete tables. My tables are also going to tell you about the product at the change to electrolyte, the product remaining in the system as the form of the remaining solution. So you are going to find my tables better since they will talk about the third one. Okay, so I am going to write the equation here for you so that it's easier for you to remember. So this H positive ion and this negative ion. Now the remember, negative ion has -2 charge. This is 2 plus. So we have to have 2 ions in order to get the charges balanced out. And hence we get H2SO4. Aqueous, aqueous, aqueous. All is aqueous. Everything can be dissolved in water. So
All
that's
right.
about it. That's the dilute sulfuric acid he was talking about. You'll find this equation in the table as well.
All right.
Now, something that is important, the reason we keep stressing about the use of inert electrode is that electrode, whatever is made up of, may affect the product you get. Sometimes the product may react with the electrode. Now, if we were just talking about this chapter, you might not know this, but since you're already done with the chapter of reactivity series in metals, you already know that in case of electrolysis of aluminum fluoride, we had electrode made up of carbon. We were producing
Right.
oxygen over here, and they actually reacted with one another to produce carbon dioxide gas.
Uh-huh.
So
Yeah.
this tells us if the electrode is inert, if the electrode is unreactive, it won't react like this. That's why we keep on stressing that inert electrodes has to be used. So every time you see the word electrodes over here, they keep on stressing the word inert electrodes. Like you have it here, right in the heading.
So what does it exactly mean?
Unreactive material. Electrodes are made up of unreactive materials so that they don't react with the uh, products over here, or
All right.
something new would be produced, right? You won't
Mm-hmm.
get what you were trying to get out of it if it reacts and produces something new,
Yeah.
right? So
Yeah.
moving on, there is an electrolysis of dilute sulfuric acid using alternating electrodes. This is somewhat different. We use dilute sulfuric acid. The word dilute means we are going to use a little amount of sulfuric acid, and the rest whole thing will be filled with water. As you can see, this whole thing is filled with water. There is a very little amount of acid in there. So when we turn on the power supply, the electrodes, this is the positive electrode, anode. Of course, this was going to produce oxygen. Why? Let's talk about this. H2SO4 is going to give us two ions. It is going to give us H positive ions. It is going to give us SO4 negative 2 ions. Now, since this was aqueous, aqueous means water. Water is going to give us H positive ions and OH negative ions. Now, the cations are same. There is not going to be any race. There is not going to be any competition. You're only going to get hydrogen over here, right? And in case
Yeah.
of these anions, we've already discussed that this one goes to the positive electrode or anode to give you oxygen. There you go. You have the oxygen over here.
Yeah. All right.
What will you be left with? Since this formed H2 at cathode, this formed O2 at anode, you will be left with this. So the purpose we go with this electrode is that we electrolyze water and sulfuric acid remains the same in this whole system. This is to electrolyze water and get hydrogen and oxygen out of water. This electrolysis is specifically done to break down water into hydrogen and oxygen. Now, if you look at the formula of water, and if you break it down into hydrogen and oxygen, right, you get
Mm-hmm.
twice as much hydrogen. Why? Because the formula of water itself says twice as much hydrogen as oxygen. So this is the length of oxygen, and you have double that length of hydrogen. This and this, right? Makes sense?
Yeah. Yeah.
Why? Because the formula itself says that there are two atoms of hydrogen for every single atom of oxygen in the formula of water. So I hope that makes sense.
Mm-hmm.
Okay.
Yeah.
Now moving on. This experiment could be used to show the formula of water is H2O. I hope that makes sense. Reactivity series. The three simple tips I was talking about are written right in here. If the metal is high in the reactivity series, you always produce hydrogen. If the metal is below hydrogen in the reactivity series, in which we only have copper, silver, and gold, you're going to get that metal at cathode. In case of anodes, the solution of halides may produce fluoride, bromide, or iodide may produce chlorine, bromine, or iodine if it is concentrated. Now, it's not mentioned over here if it's concentrated. And in all other cases, you're going to produce oxygen. So most of the time, you end up with hydrogen on cathode and oxygen at anode in case of aqueous system. Most of the time.
Mm-hmm.
Now, this leaves the problem of something moderately reactive, such as zinc. But at IGCSE, you don't have to worry about these examples because you won't see these examples in IGCSE. So yeah, moderately reactive stuff is uh, is something difficult to deal with, is a complicated concept, but we don't deal with that in IGCSE. We keep the simple and easiest stuff for IGCSE and any complicated concept for advanced levels.
All right.
All right.
Yeah.
So this is the kind of products that you get for cathode and anode. The same stuff is given in the document that I've given you, and going with that document would help, but that document might have mistakes. So if you are confused with the mistakes over here and there in the document, you can always ask me because you are going to find some mistakes in there. This is done by
All
a
right.
student, not by me. So definitely there would be some mistakes. Getting back to the book, there is a small topic of what would happen if we have non-electrolyte system. Of course, you won't be able to run electricity through them, so nothing would happen.
Mhm.
All
All
right.
right.
So we
Yeah,
can't electrolyze covalent compounds because electricity can't flow through them. We can't electrolyze non-metals alone because electricity can't flow through them. We cannot electrolyze an ionic compound in solid form because electricity cannot pass through it.
they are tightly packed.
Yeah. So
Mm.
the key point is there may be some exceptions to these rules. There are some covalent compounds that are electrolytes. Water, acid, ammonia are the examples of those. But we have catered those examples above. You have an example of a sulfuric acid right over here, so this should make sense.
Mm.
The last topic that we are left with is quantitative electrolysis, but I suggest we do it in a separate setting. First, it's about time, so let's call it a day.